I'm excited to be in this forum and talk about this topic. The main idea I'm going to talk about is motivated by research that I'm doing in history and archaeology, mainly. And the unlike physical problem that originate from physics, the problems that we deal with are lacking in models. What we do have are data points. And the basic motivation is to infer the model from the data points. So it's like turning the bowl upside down. Normally, we see manifolds when we have a good model, like a set of equations or something like that. But in our case, we'll see that there are no sets of equations for the problems that we're trying to tackle. What we'll try to do is use the data points to infer a manifold, to learn a manifold, to estimate one. Okay. Okay, so the talk will be divided into several parts. The first part will be about the historical investigations. It would be about motivation mainly, and it will be very non-mathematical. I will try to describe a project that I was part of, I am still part of, tackling various questions regarding literacy in ancient Judah and Israel. Then I'm going to try to convince you that this project led me to explore estimation of manifolds and how these two things relate. So the second part of the talk, well, supposed to be most of it, if there will be not too many questions, it will be most of the talk, will be more mathematical, formal, talking about the mathematical problem behind the scenes and what the results that we can obtain, okay? So other than these subjects, I'm just so that you know me, because I've not talked in this forum before. So I have some works on art history as well, all sorts of signal processing related works. I'm doing math therapy. So if someone is interested with that oxymoron, I'm doing that as a volunteer for the last decade or so. So I will be happy to take this offline. And I'm a flute player. So please check me out on YouTube or whatever. And I have two kids, two wonderful kids, which I should update this image because it's already, they're much bigger now. Okay, so that's me. That's about being sober. Now let's talk a bit about history. So this gate is gonna accompany us. It's Nebuchadnezzar's gate, the gates of Babylon, Ishtar gate. And Nebuchadnezzar is related to the talk. So this is why I chose this as my gate for this talk. So let's talk about this project. So just to set the historical stage, we're talking about First Temple period, starting with King David, of course, around 950 BC. Then David is being replaced by his son Solomon, of course, who finishes the first temple. He builds the first temple, right? And after his death, there's a succession dispute, right? And we have a split into two kingdoms. We have a northern kingdom of Israel and southern kingdom of Judah. The northern kingdom of Israel, which was the more prominent one in the historical stage, is being destroyed by the Assyrian Empire at 700 BC. We'll discuss this empire, this northern kingdom as well. And the southern kingdom is being destroyed by King Nebuchadnezzar, which I just mentioned, by Babylon at 586 BC. So the Dead Sea Scrolls are something which is outside of our scope. We're going to speak about First Temple period literacy, not Second Temple, which is the Dead Sea Scrolls. So when we want to discuss literacy, we should discuss the written evidence. So most of the major texts that was written at the time were probably written on papyri. But unfortunately, there is not many papyri surviving from that time because of the humidity. There's only one, and you see it in front of you. So these just few letters in ancient Hebrew cannot tell us much about literacy, right? Or literary activity. So it's not suitable for this task. maybe we can go to discuss monumental inscriptions like this stela of Mesha, king of Moab, or others, but like Tel Dan inscriptions, Tel Dan stele, but we have just a handful of these. So we cannot, so it's just a handful of authors. So what can we say about literacy at that time? So this is not suitable. What we do have are ancient sticky notes, which is Ostraca. It's written with ink over clay material. And these we have several hundreds of. So we have data for this. It's more mundane material. So it's not very sophisticated literary activity, right? So you bring me this and this flower, or bread and wine, stuff like that. That's the content. Sometimes it's about movement of troops, not more than this. And the historical stage that we were testing. So we found a very nice site to test these, to test literacy using such inscriptions, which is the Arad fort. So now we're talking about, let me use the laser screen. We're talking about Southern Kingdom, nearing the end of the first temple. So it's around 600 BC, before Nebuchadnezzar destroys Jerusalem. And the south, the site is Tel Arad, which is in the Beersheba Valley. It's a small site, around 20 or 30 soldiers. And we have around 100 inscriptions in total. We were using around 18 of them, which had enough material. And I'm going to try to convince you that some small site in the arid desert of Judah, of the southern Judah, is a good site to understand literacy in general. It's easier to learn from remote sites than from the capital city. And I'll try to explain why this is a better site to learn from. So the algorithmic apparatus was going along these lines. First, you take the characters, which are not very well preserved, as you can see, and you do some sort of characters restoration. Then we do some features extraction and distance embedding. And then we do some hypothesis testing to decide whether two given inscriptions were written by a single author or maybe two authors. So that's the algorithmic apparatus, and I'll discuss it very shortly. So why do we need to restore them and not do binarization like is normally being done in image processing? Because as you can see, the signal is very weak. And when you try to binarize it automatically, we even tried to develop some binarization algorithms, but we failed completely. Well, not completely, but not sufficiently well. This is not a good reconstruction to do something serious. So we had to compromise and go for a semi-automatic reconstruction. So the idea here is that we have some cost functional that we want to minimize. If you know active contours in image processing, it draws inspiration from this. So you have an energy functional relating to the image itself, trying to adhere to the image, and you have an energy functional minimizing curvature. And then you do a piecewise linear spline, so a user samples points, key points. You do a piecewise linear spline and do some gradient descent to optimize this functional. And then you can reconstruct strokes. And from the strokes, you can combine letters. So that's the general idea. This was done in my master's thesis. Then, when you have two inscriptions, you first.
Barak, can you explain the previous slide a bit more? What the notation is?
Okay, so I don't want to get into too much details because I have the math part of this talk will be on something else. So it's just a mentioning. But the idea here is you sum over the gray levels normalized by the radius. So you see you have like a sequence of disks. It's a curve of disks, right? So you sum over the gray levels and normalize them, and you don't want the radius to shrink to 0. So there's a reason why this is square root of r. We had to analyze this, and this is just intrinsic curvature of the curve of the medial axis curve. Okay.
Okay.
Okay. So now you take two inscriptions, you reconstruct their letters. So here I reconstruct Aleph characters, and as you can see, there aren't that many. But then we take these characters and we forget where they are coming from. So we construct the characters and then we do some feature extraction. So we're now in a vector space. Each character is represented by a vector. And we can do brute force of k-means with k equal to. So we have a null hypothesis. The null hypothesis is that the characters were sampled from a single distribution. And we want to negate this. So now if I do clustering based upon their features, the clustering should be random. I can quantify this. So I can quantify how similar they are to the original ones. And so let's say I have two clusters now, okay? I can ask myself, how similar are these clusters to the original inscriptions? Okay, and this similarity is something that I can measure. So if I have something that occurs at random, I can compute how likely it is to get something which is that homogeneous. Okay, so we can measure that and give a p-value for this null hypothesis. And if the p-value is too low, we negate the null hypothesis, and then we know that it's not a single distribution. It's coming from two distributions. So what's special about this algorithm is that it is very well adapted to small data. Normally, when you do hypothesis testing, you need to have much more samples to say something meaningful. And with this algorithm, you can say meaningful things even when you have 6 against 5 characters like this. But now I can do this test for Aleph, for Bet, for Gimel. I can do this separately, and I have many, many independent tests, which I can then combine their p-values and get something more significant.
Barak, how do you weigh the different features?
So
to create a distance, I guess, for clustering.
Oh, yeah, I combine them all, I concatenate them into one long vector. But it's more, well, it's more complicated than that. So we take, each character is being characterized by its distance from all other characters by all features that we tested. So it's a very long distance. It's a very long vector. That's the vectorization process. But I'll say something that this statistical procedure, this hypothesis test, is blind to your choice of features. So if your features are irrelevant, then the hypothesis test, you will not be able to negate your null hypothesis because you will not see the difference between distributions. Okay, so if you do not negate the null hypothesis, you're agnostic. You don't know what happened, right? So you do not say that the null hypothesis is true.
I'm missing the logic behind what you're doing. So it's the logic, because you're comparing a letter at a time, you're comparing the entire text, assuming that the entire text has been, yeah, but I mean, you have dependent claims because all the letters, say, at least in a given word, should be written by the same person. So if letter clusters by the person who wrote them, then actually all the letters in a word should cluster to the same cluster. So you can't really do independent tests whether the clusters where you have 1 or 2 or 3 cluster on each letter by itself.
No, well, okay. When I say a letter, I mean all types, all characters from a type Aleph.
Yeah. I mean, but if somebody wrote Abba, then the bet of the Abba and the Aleph of the Abba should. So I mean, if you have 10 bets and 10 Aleph, they should cluster to the same clusters. If we argue that the clusters represent handwritings.
So why do you think that the bet clustering should depend on the Aleph clustering?
So that's what I'm trying to understand. I mean, what's the logic behind clustering letters at all? I mean, I would guess you would imply.
Okay, so the logic is this. I'll try to say something like that. So now I don't know which letter came from which inscription. Okay, I threw them all into one big pile. Okay, I just take their features. I do some. Now I have mathematical representation of each character, and I don't know where they're coming from. And I let the computer decide which letter comes to give me 2 clusters. I'm not saying to which inscription specifically, but it clusters into 2 clusters. And then I want to measure how well these clusters are with respect to their origin. I know their labeling, okay? The computer didn't know when it did the clustering, but I know their labeling. No, so now I can ask myself, okay, how similar is this to the original clustering? So if it was one writer producing all Alephs, I would guess that this clustering here would be random, right? So you get two clusters which are randomly assigned, right? So it should not.
So that's what I assume. But in this case, then when you're doing a test, the test on the bet and the test on the Aleph is basically on the same zero assumption that manuscript A is from author A and manuscript B is from author B.
So the null hypothesis is, formally speaking, is that the Alephs come from a single distribution, which the k-means cost function is suitable for. So the null hypothesis is different for each character because you conduct this experiment independently for each letter type. We can discuss it more later.
Yeah, we can discuss it later. That's getting technical.
Yeah, okay. But then I get a p-value okay, so I get a combined p-value from all letter types. Okay, so I combine these tests, and now I have a p-value for two given inscriptions being from the same distribution, from the same single author. And then I can build a graph, which an edge in the graph means that these two inscriptions were written by separate authors. And then if I find the largest click in the graph, this gives me a lower bound to the number of hands that should exist in the corpus. Because if I have 5 pairwise distinct inscriptions, then I need at least 5 authors to produce this. Then we know that we have several distinct hands sitting in the Arad fort from the text, from the context. And then we can look at the writers of this context and see, okay, there are lower ranking figures that are literate. And that made a lot of noise when we found that. By the way, this was verified later by a forensic expert. This was a publication from this year. So we let a forensic expert do the same tests on this specific Ostraca.
So then, Barak, I guess you get a matrix for each letter then.
What?
For Aleph, you get such a matrix.
No. Okay, so I have, yeah, in theory, you're right, but I can combine the p-values into a single p-value because these are independent tests. There are statistical ways of combining these p-values into a single p-value. Mm-hmm. So instead of having, say, 5 or 6, because I have Aleph and Daled and Hey and Vav, now I have one single p-value that represents the likelihood of these two being originating from the same authorship. In this sense, I'm using the same hidden hypothesis, which is a single author. Okay, then we took this mechanism. This is a more recent publication from 2020. We took this mechanism 200 years earlier to the site of Samaria. So getting back to the historical stage, so this is the capital of the Northern Kingdom. So the last test that I described was in the Arad fort, which was some in the arid desert, in the margins of the Judean kingdom. Now we're talking about the capital of Samaria. So if you have many writers in some remote site, this does give you a hint at the literacy in the entire administrative apparatus. Whereas if I would have found in Jerusalem many writers, this doesn't say much. Well, doesn't say as much, at least. Now we went to the capital of Samaria, which has the major corpus for the 8th century, and we played the same game. And we thought that, so this is like the time when the Northern Kingdom is at its peak. And it was mentioned by the Mesopotamian empires. It's a meaningful empire. It's a meaningful kingdom. So we figured that among 30 inscriptions that we tested, we'll find many authors. But this didn't happen. So the separations graph looked like that. And then we didn't know what to make out of it. So how do you make this lemon a lemonade? What can I say about this? Because this can have two possible interpretations. Either there are not many authors, or we don't have enough data, because it's not, if I don't negate the null hypothesis, I don't prove it as well, right? So it's not symmetric, this hypothesis testing. And the Sumerian inscriptions are smaller than the Arad inscriptions. So what we could do to figure this thing out, so we said, okay, if we had known what is the likelihood of getting a separation by accident, because it can happen by accident. This is a statistical test, and things that are random do occur. So if we knew what's the likelihood of getting a separation in our graph by accident, and then we could try to understand maybe what's the maximum likelihood of number of authors. And that's what we've done. So how do you estimate your errors? You need to take a corpus which has similar characteristics, where you know what's the ground truth, and then evaluate your error on that. So the way we've done that, we took inscriptions from Arad, which are much longer, and broke them into pieces. Well, not really, on the computer. So now these 4 inscriptions, I know that they were written by a single author, right? They're not really 4 inscriptions, but I can separate their characters. And I can now play these games and try to understand what's my error rates. After having the error rates, I can estimate the distribution of the number of separations given 1 writer, or 2 writers, or 3 writers. So how will this graph be populated by red points, right? So I can have the distribution of 1 writer, 2 writer, 3 writer, et cetera, et cetera. And then I can derive the maximum likelihood estimate. So that's what we've done. And the maximum likelihood estimate for that case was 2 writers with confidence interval of 95%. So we have these 2 negative ends. In the 8th century, the kingdom of Israel, the capital of the kingdom, we have 2 authors, by the way, for a corpus written over a 7 years period. And in the Arad fort, over 1 month period of time, that's from historical consideration, we know, you have many authors. You have at least 5 hands just by statistical analysis, mathematical analysis. Okay, it doesn't mean that literacy was not widespread at the 8th century, but it means that at least the government was centralized. And another implication is that the major evidence of written material from the 8th century BC of the entire Israel region is a handful of authors. And that's a significant find. It's a negative find, but it's a significant find. Okay, now let the history begun almost, and let's go to so this was the inspiration, and I'm gonna try to convince you that this relates to manifolds. And then I'll try to explain how we're using this manifold model to do similar stuff on different data. Okay, so when I talk about manifold now, I'm going to talk about the differential geometric object. So we have some object that we can have chart for. We have an atlas of charts, and we have transition maps, which are smooth. Everything is smooth. We're talking about differentiable manifolds. And normally when we encounter manifolds, we have a set of equations or some model or something like that, right? So where do I find them in history? So let's go back to this character restoration process, right? So the user samples some key points, and then we create a spline that goes through these key points, right? So, and this spline is interpolatory. So it's interpolating these key points. So now take the minimizers of this and now try to play with the interpolation points. So I can take this point and I can move it a bit here or there. Think about how we are working with Illustrator when we're working with spline or Bezier curves. When we're moving the control points, right, we change the shape just a bit. And the control points gives us a parametrization of that shape, right? So we have a parametric space. So I can parameterize the variation of letters in this way, right? Not all variations are legitimate variations of this. This is the Vav character in this case, but not all variations are legitimate. So we have a lower dimensional object there, which is sampled somehow. We have samples of it, right? So each letter now is a sample drawn from some underlying manifold, which I don't know. But each letter is a sample of that. Now, if I could infer this manifold, maybe I could try to understand all sorts of things about the distributions over these manifolds, or even better, if I can create random walks on this or stuff or things along these lines, I can create evolutionary models like I do with biology. So, but here I don't have DNA, I have shapes. It's evolution of shapes. So maybe I can do evolution of writing. That's something that I would like to investigate. And then after building this, so handwriting was my inspiration. I started working with manifolds. And when I got to Duke, I saw that the group that I'm working with, the group of Ingrid Dubschi, are working about evolution, on problem of evolutionary morphology. And they were working with lemurs, or more accurately, with lemur teeth, molar teeth, okay? So we're talking about the molar teeth of the lemur. And they have many samples of these teeth. And they try to do all sorts of things with these teeth. Basically, to understand the evolution of shapes. Like I just described with letters, they're doing with shapes. And they have a lot of work about registering surfaces, registering the surfaces. And then in the discussions that we have in our group meeting, the biologist, the paleontologist asked us the following question. Given, say, I have samples from group 1, group 2, group 3, and group 4, can I say something with statistical confidence that says that these groups are well separated? Can I maybe do some sort of null hypothesis testing like I just described? They don't have many samples, just like the problem we had with the Ostraca. We don't have many characters. They don't have many teeth. They have, I say, 10 or 15 from a given species. Or they found a new tooth, which has lots of historical implications that they want to understand to which group it belongs. They know that it's one of these 4 groups, but now it matters a lot. It can change the idea of when lemurs migrated to, it can change the dating of when primates migrated to Madagascar and then turned into lemurs. So now that's another question that they wanted to answer. When you do statistical tests, the go-to method maybe is the t-test. But for t-test, you would need some sort of understanding of the distribution. So you need to, maybe you have it beforehand or you have enough samples to assess it. But in any case, you need the mean because this is what it measures in some sense, factoring the variance inside as well. And even in our case, when we were designing this algorithm to work with small data, we still need the mean because we do some sort of k-means with k equal 2. So we need to be able to compute means of these shapes. But these shapes are represented by point clouds. So each shape is now a point cloud in R3. Let's say 1,000 samples in R3. So it's, and they are registered. Okay, so it's points in R3000. They are registered by other algorithms that were developed in our team and were verified by the biologist. Yeah, of course.
This is maybe a good point because I missed that also when you map from letter shapes to RN. So what is exactly how does the mapping work?
From the letters? So the letters you
can... From a shape, like a monolith or a letter to RN.
Okay, so let's talk about these surfaces because I'm currently here. So now you have points sampled in R3. You have 1,000 points, okay? Sampled from a tooth, from a given shape. They are registered. You have correspondence mapping between them, and you can normalize them, say, by the surface area and center them around 0. The center of mass around 0 and normalize them, and then you register them. So I have correspondent, you see the colors of the surfaces, right? So this purple, it corresponds to this. I have correspondence between these shapes. So each sample has a correspondence across all shapes. Okay.
Corresponding to the normal, you're basically
no correspondence across shapes. So this shape is aligned with this one in the sense that you see the colors. The colors represent similarity. So when I talk about this specific point, I know they are ordered. They're well ordered in the sense that this corresponds to this. The yellow corresponds to yellow. Okay, the colors here in this figure represents their correspondence. So I have, let's say I have 1,000 points, but they are ordered. I know which corresponds to which. Okay, so this is an embedding, right, in our 3,000 in some sense.
So how are they chosen? Is it uniformly? I mean, are they random? I mean, how do you? I guess that can affect later your analysis.
Yeah, you have distortion in the embedding for sure. They are very densely sampled. That's so. How are they measured? By a CT scanner, micro CT scanner, which scans the tooth. It's how are they sampled from the surface itself? It's a good question, and how well it does really fit. So there might be small distortions in that, but if your resolution is fine enough, then the distortion is limited. Yeah, there is a limitation there in the specific case of teeth. You're right. But then these are objects in very high dimensional domain, and if you want to do statistical tests, we have a problem, of course. But we can perhaps use this idea of manifold to reduce the dimensionality, at least on the local level. Okay, I'm not going to explain exactly the gist of the things, but then if I want to compute mean on the manifold shape, on the manifold of the base shape manifold, I can compute the Frechet mean. But to compute Frechet mean, I minimize the sum of squared geodesic distances. So it's finding the point on the manifold that minimizes squared geodesic distances. So I need to compute geodesic distances. So again, I have this same image of, I have a point cloud sampled from some underlying manifold. In this case, we did some estimates to estimate the intrinsic dimension. And then we need to be able to compute geodesics in order to compute averages and then perform hypothesis testing. So that's the general idea. I'm not going to discuss this. I'm going to discuss just the math of approximating the manifold and geodesics from point clouds and noisy point clouds as well. So if I have noise as well inserted, okay, that's going to be the math part of the talk from here on to the end. Okay, so approximation of manifolds. Normally, when you read about manifold learning, so if you look in Wikipedia, you'll see that it redirects you to nonlinear dimensionality reduction. The idea in nonlinear dimension reduction is that you have a nonlinear object and you project it onto some Euclidean domain of the intrinsic dimension. That's the gist of it, or maybe a bit more than the intrinsic dimension. The problem with these approaches is, what do you do with this? How do I project this into R2? So I can try, of course, but there is no optimal way of doing that, of course. And so maybe you can try to preserve the norm if you go to some higher dimensional domain, but not really easy to understand how. So there are ways of doing this through kernel operators, like the diffusion maps or something like that. But then it's not clear what the dimension of projection should be. There are some limitations there. But once you go to the linear domain, you can operate with linear algorithms on low dimensional domains, and problem is solved, so to say. So I would like to suggest an alternative. Do not project it, estimate it. You will not work as fast as working on a linear lower dimensional domain, but you can work in the ambient space. The ambient space might be of a very high dimension, but the intrinsic dimension should be low. And then I'm going to give you a computationally feasible way of working on these point clouds on the underlying manifold. So how do we do that? So the problem is like that. It is along the following line. Instead of M, I get a set of samples. These samples have some resolution parameter that we call the fill distance. The fill distance is corresponding to the radius of the largest ball that you can put inside your data, okay? And you have another parameter, which is separation, which allows you to understand how well these points are spread across this object. So in order to understand how well the points are sampled, the parameters I'm going to use in my analysis are fill distance and separation. But then I don't have the manifold itself. I have only the point cloud, okay? Point cloud, and I say I know the fill distance and separation, though I don't really need them, but I need to estimate the fill distance in order to understand how to work with it. From the point cloud, we build an approximate manifold. And then we can ask ourselves, okay, is this object truly is a manifold? How smooth is it? Can we say something about its smoothness? And can we measure how close it is to the original one? Will it converge to the original manifold if I have more and more samples? Will it preserve the metric? Because if I want to compute geodesics, I need this object to preserve the metric as well, right? In some sense, to be almost isometry. So these are the questions that we're trying to answer, okay? In recent years, there is a growing interest in this topic in general. Most of these methods are either putative or do not have a computationally feasible way of working in high dimensions, though some of them do have in recent years. First one was in 2014 that said that they're linear in the ambient dimension. So our algorithm is linear in the ambient, that has linear complexity dependency on the ambient dimension, but I'm not going to get into the algorithm in details here. But I'm happy to take this offline if someone's interested. So another term which is essential when you do estimation of manifolds is the manifold's reach. So the manifold's reach is a concept inserted by Federer at 1969. It's in the context of geometric measure theory, but it's very useful when you try to estimate manifolds because you have distribution over a manifold, right? So the reach is the radius from which you have a unique projection. So as you can see, this point does not have unique projection. I can have two projections to the manifold. I mean, projection onto as a projection in the Euclidean sense onto the manifold object. So this reach is being determined by local curvature, sectional curvature. It bounds the sectional curvature, and it bounds the way the manifold is being folded, right? So that's the concept of reach. So here the manifold is this curve, right? The boundary curve is the manifold, and now I can see what the reach of that is being determined by here. It's by the curvature, but if I didn't have so curvy corner here, then this would determine my reach. So my sampling resolution or the noise amount of noise that I can allow, of course, is being limited by the reach. So this is how we constrain our sampling assumptions. So what are the sampling assumptions that we allow? First, we want this fill distance and separation to be bounded. Okay, so the fill distance should be such that it is bounded by some constant times the separation. This means that it's quasi-uniform in the deterministic sense. Then I require that M is K times smooth and it's compact and boundaryless. Right? The algorithm is local, so the boundary is not a case that I trouble myself with. Next, the reach should be bounded away from 0. And the noise is bounded by half the reach in order to produce an approximate. And the main concept that we're using in the analysis is moving least squares. So what is moving least squares? It's an it was born as a way of estimating and approximating functions from point clouds, from sample points back in the 70s. The idea is that for a given point, you do a local polynomial fit, and you evaluate this polynomial at x, but you do it for all points in your data set, all points in your x domain. You evaluate this different local polynomial, and then you have an underlying object. This underlying object is a function, of course. And in 1980, Stone investigated how well it approximates the function and how well the derivatives approximate the derivatives of the function, the underlying function, the sample function, given some noise. And in 98, Levine showed that this approximate is smooth and has a high approximation power when we have clean samples in the approximation theoretic sense. So a generalization of this approach would be what we call projective approximation. So we have a point cloud. Now it's not a function. You don't have a clear domain. And you have, so the samples are the blue points. That's my labeled data, let's call it like that. And then I have some new points, red points, and I'm looking for a procedure that will project me onto an approximating object, P of R. And I call this projective approximation if a projection of the projected object gives me the same point that projected, the originally projected. So for surfaces in R3 basically, but codimension 1 in general, this method works. Levine proposed a method that goes along the following lines. For each red point that you want to project, you find a local coordinate system, then you do a local polynomial fit above this coordinate system, you evaluate this polynomial, and you do it for each red point that you want in general. So for each red point, you'll have a different coordinate system, and then you'll do a different polynomial fit, and you should have some approximating object. Okay, that was basically an algorithm that Levine presented in 2004. So for a general codimension, we generalized this, but not only did we generalize this, but we defined this was part of my PhD thesis, we defined what the approximating manifold is. And the approximating manifold is take the original one and apply the projection onto the original one. That's the approximating object. And we have all sorts of properties of this object. So we can say that it is a manifold. I'll soon quote the theorems about this object. And how do we find a coordinate system in the general codimension problem? So the idea is along these lines. So for each point, I'm looking for an origin and direction. So I'm looking for an element in the Grassmannian as well as a point in the ambient space. And what I wish for this coordinate system to do is that the squared Euclidean distances, squared Euclidean distances centered around Q. So this theta is a weight function that centers me around this origin Q, okay? So I want something that the weighted sum of square distances would be minimized. The affine space, this affine space should minimize this quantity. However, as you can see, the point R, the red point, does not appear in this minimization. So, it's a constrained minimization. I limit ROI and data proximity. These two conditions are not very important. What is important that ties me to this point is this property. So I have another constraint, which is that the line between R and Q should be perpendicular to this element in the Grassmannian, to this directions. And this is a very crucial condition because it's a generalization of the projection, of the Euclidean projection onto the manifold. Why do I say that? Because if Q were a point on the original manifold, but say the projection of this red point, of this R, and H were the true tangent, then this condition would have been fulfilled, of course. And this condition says, in some sense, that the true tangent and as well as the true projection are in my search space in this minimization. And we can harvest this to show all sorts of properties about this approximating planes. Just an an eye-pleasing example. So before I go to the theorems. So now I sample this manifold. Now these are images of airplanes, rotated 360 degrees, one rotating angle, and they are unorganized. They are embedded in high dimensional domain. I have roughly 1,000 samples of this. So now I can try to create a curve on this manifold. So it's a one-dimensional manifold, right? So it's just rotating the camera. So I have one parameter controlling this. It's a curve in high dimensional domain. So now I can try to create a curve on this because they're unorganized. They were sampled from this curve. Now I can try to create a path over this curve. How do I do that? I find this, let's say, estimate of tangent. Then I do a small step and I project. Small step, project, small step, project. I can create a path like that. And here it is. Here is the path. You see it in front of your eyes. These are interpolation points, of course.
Barak, is there any tolerance for outliers?
Yes, because you have ROI. I didn't get into the, so you need to measure your, you need to decide what's your region of interest. And so you remove points outside the region of interest. And so there is a, but I said, I'm not getting into the details of the algorithm.
Yeah, yes, okay.
Okay. What can we prove about this object? First thing we can show is that given that this weighting is smooth and I bound my distance from the manifold for the starting point, I bound this to something bounded by the reach, then my projection will yield a point on a C infinity d-dimensional manifold almost everywhere. The reason why we have almost everywhere because we're using Sartre's theorem somewhere in the middle. And this approximating object is a manifold of the right dimension and it is smooth. What else we can show that it's close to the original manifold in the Hausdorff sense, in the Hausdorff norm, up to h to the power of k. I remind you the h is our resolution parameter. So we have this bound as well. And then we can use this idea to approximate functions over the manifold. Very simply. Why? Because for this given point, I find this local coordinate system. Now I can use this local coordinate system as a local pullback, and I can estimate this function. Instead of working in the ambient space, I can work on the intrinsic dimension. This is this h, this coordinate system is from the intrinsic dimension. So I can estimate a function from a low dimensional domain to the target. And we can show that this approximant is smooth as well and has high approximation order. So when I say high approximation order, I want to stress that h to the power of k is theoretically optimal. So you can show that you cannot do better than this asymptotically, given that this is your sampling resolution. Okay, but this curve, now this function over a curve is now defined over a tubular neighborhood of the manifold. So say that this is the clean manifold and a function is the color, okay? And now the sample set that you're given is a noisy sample of the manifold. It's in a tubular neighborhood of the manifold, and the values of the function are noisy as well. That's the resulting approximant of the manifold and the resulting approximant of the function of the manifold as well. Okay, now let's turn to a more recent work about geodesic approximation. So what we can say about this approximant in the geodesic sense, in the metric sense. Normally, when you have point clouds in high dimension domain and you want to measure geodesic distances, what you do, you would use Dijkstra algorithm, which goes along the following line. So I have point cloud. Now, for each point, I take an epsilon neighborhood. And in this epsilon neighborhood, if I find other points, I connect them. Okay? So now I create a graph of connectivity on the point cloud. Now, given 2 points, I want to measure the distance between them. I take this metric graph and weighted by the Euclidean distances between each 2 points, right? And I can look for the shortest path on the graph. This is a standard way of estimating geodesic distances over manifold from point clouds in high dimensional domain. The problem is that it doesn't work very well. Okay, so back in 2005, Memoli and Sapiro showed that its convergence rates are h to the half. If you have a meshing of the manifold, then, well, at least in codimension 1, you can construct methods that have H convergence, O of H convergence. There's a very famous work by Kimmel and Sethian from 97 about that. And empirically, I saw some works that claim H squared, but they cannot prove anything. So the question is, can we do better using this idea? And the answer is yes, we can. How much better? Much better. I'm going to show you how. So say I have this sparsely sampled point cloud. What I can do, I can construct a local tangent. I can sample a grid on this tangent, and then I can project it using this mechanism that I showed before. So this is actually resampling of the approximating manifold. I can sample the approximating manifold, and since I have a procedure, I can sample it as dense as I would like. Okay, so the algorithm that I would use here is sample it to epsilon precision, and then find the shortest path on the metric graph. You do the Dijkstra on the resampled shape. So instead of having this picture, what we get is this picture. So now you see that the new shortest path is much closer to the original geodesic. And what can we prove about this method? So essentially, what we were doing was we were sampling the underlying manifold, the approximating manifold, and then computing geodesics over this, because since I have there up to epsilon precision, I can get the geodesics distances up to epsilon precision. So the question that needs to be asked is, how close is the manifold moving in its squares to the original manifold in the Riemannian metric sense? That's what we try to answer. And the answer is that the geodesic distances are preserved up to O of H to K minus 1. Here, I don't know that these are optimal rates. There is no work about this, but I think it should be optimal rates, because a curve is an integration over the derivative. The length of a curve is an integration over the magnitude of the derivative. And when you approximate the derivative, you have to lose an order in optimal rates. In optimal rates analysis, you can show this. And what happens when we're adding some noise to the problem? So when we're using very low levels of noise and we measure relative error, what we observe is if you compute the Dijkstra on a noisy point cloud with very small amounts of noise, you get very high relative error. It's so high that even if I take Euclidean distances between points in the ambient space, I get better approximates of the geodesic distances. Better approximates of the geodesic distances than the shortest path on this graph. But if I resample the degree 1, local degree 1 manifold, or local degree 3 polynomial degree, I clean out this noise significantly. And here is a not so trivial manifold. It's an ankle bone that we want to compute the shortest path. So it looks like this. So the green is the reconstructed after resampling. The red was the original path. Okay. So what happens with noise? So all these estimates up until now, we're discussing the problem of non-noisy estimation. So you have samples you have clean samples of the manifold. What happens if you add noise? That's a much harder problem to show convergence under noisy samples. So a phenomenon that we observed was that it works extremely well with noise. And we figured out that there must be a reason why this is so. So this is a real example, what you just saw. And this cannot be coincidental. because we see it in the geodesic approximation as well, right? Although the guarantees are for clean samples, we have convergence with noise. It seems so, if you have enough samples. And when you do function estimation in the noisy case, then say I have a function, theta, which is ck, smooth, and I want to estimate, say, the mth order the derivative of that, or mth order differential function, functional over it, okay, evaluated at 0. So it can be either the value itself or some tangent, okay? And I construct an estimate based upon finite sample, n samples. Then what I actually estimate is the regression function, which is the expected value at each x, okay? So you have noise in the y domain, and you go along the x-axis, and then you estimate. And apparently, you can reconstruct you can reconstruct from the point cloud without knowing what's the underlying function. You can actually reconstruct this function when n tends to infinity. So you need to have enough samples, and you will have it. Okay, that's a known result from statistics. I'm not going to get to optimal recovery rates because we don't have time for that. But there are ways of pronouncing what's the optimal rates. And Stone showed that the optimal rates are this, and that the moving least squares for function estimation obtain these optimal rates in probability. So the rates are in probability, of course. It's order of convergence in probability. And Stone showed this for the functional case. What happens about, what about manifolds? So it's not clear what the optimal rates are. There are some method that tries to work with the noisy point cloud and produce an approximating manifold, but in order to show convergence, they have to assume that the noise level decays to 0 when your sample size tends to infinity. Otherwise, they are not able to show this. And we have a proof that we can show convergence. The noise model is that the manifold is the blue curve, and it's sampled in a tubular neighborhood, uniformly from that tubular neighborhood in the ambient space. And of course, we have to bound the level of noise with the reach. So it cannot be, it's bounded, the proportion between noise and reach must be bounded, must be small enough. And we have the following result. So we reconstruct the rates of convergence for points on the manifold, the optimal rates in the sense of function estimation. I'm not sure that these are optimal rates for manifold, but I have a guess that they are. And for tangent estimation as well, we get the same rates of convergence. Again, in probability, when n tends to infinity. We don't have time for interesting observations from the proofs because time is over. And looking to the future is I'll just say in a few words that the picture for working with shaped manifolds is that it's not really a manifold. It's probably a collection of manifolds and with varying dimension and probably intersecting. So there is much work to be done on these more complex scenarios. And
that's all, folks.
Okay, thanks very much for a fascinating talk. Are there any questions?
Yes, I have a question. So how does the number of parameters that you need to find to fit locally to do the least squares, I guess, grows quickly with the dimension, right? Both of the
intrinsic
and
just the intrinsic dimension. Yeah. The number of the local fit is in the intrinsic dimension, not ambient space.
The local fit, yes. So so how does the number of parameters come into the analysis?
So okay, so I did not mention this, but if you are using a local degree polynomial, say 1, then the number of parameters that you need, the minimal number of parameters that you need in a neighborhood, in an O of H neighborhood of your sample, should be the intrinsic dimension plus 1, because you have the constant term as well, right?
Mm-hmm.
And if you have dimension 2, so you have, so it's becoming like n over k. That's the way it grows, depending on the local polynomial degree that you want, right?
Right.
So it's n choose k with, so it's the intrinsic dimension plus the polynomial degree.
Yeah.
You have there. So the degree, the intrinsic, intrinsic dimension plus degree over the degree. That's
so does it deteriorate quickly with the dimension? I mean, how?
So the dependency of the intrinsic dimension is very strong.
Mm-hmm.
So it's exponentially strong in that sense. So then if your intrinsic dimension is large, then I would not use anything more than locally linear, right? So, but locally linear does not mean that you lose the fact that it is a manifold, and that does not mean that you lose your smoothness, because this is being determined by the weighting, not by the. So it's infinitesimally locally linear, right?
Yeah.
So you lose the approximation rates. That's where you pay.
Mm-hmm. Okay, so something like the letters, if you have a point manifolds in with the feature space, it can grow very quickly, right?
Again, sorry.
I mean, if you're thinking about looking for manifolds in a feature space, it can be quite big.
Well, the feature space is the ambient space, so it depends on the intrinsic dimension.
Right, but you don't know what it is. I guess it's.
But you have statistical methods of estimating intrinsic dimension. So you can do this as a pre-processing step, of course.
Mm-hmm.
There is a work by Peter Bickel, and there's another one, I think, by Pfefferman from 2017 or something, about estimating the intrinsic dimension.
Okay, can you use your method somehow to evaluate the intrinsic dimension also? I mean, like to see how well it fits, how if it doesn't work, if it works. I mean, how maybe.
I have heuristics, but I don't have guarantees for that. So I did play with this. I'm guessing that there should be ways of finding discontinuity as well, because there is there are some nice works about function estimation, function approximation, that you can find point of discontinuities and fix your approximation in these points. So I guess that this can be generalized to the manifold as well.
Okay, thanks.
Any other questions?
Yeah, okay, go.
No, go ahead, Yoram.
No, go ahead, Jeremy.
I'm wondering how well your manifold moving least squares techniques can distinguish between smooth manifolds and things like X's, manifolds with singular points in which.
Yeah, so I said that currently it's not built in such a way that it should distinguish between these. I think there should be a way. Why do I say that I think that there should be a way? Because there is a way of doing that using moving least squares methods in function approximation. So I worked on that, and it should be generalizable to the manifold domain. But I haven't done this work, so I'm reluctant to say that I'm sure of it. But so currently, what you'll observe is that you smooth out this point of discontinuity, say, and what you'll get there, that in these points you'll get a much larger error.
All right.
Okay. Other questions?
Yeah. So in your original effort to compare or define the distance between two surfaces, how is your work standing compared to more supervised methods that would actually take samples that are classified to belong to the same, I don't know, animal or host or anything like that, and run them through a neural network that would try to separate them? And the actual neural network would define a projection de facto of each of these samples.
Yes. So the problem that I see with neural networks, so I'm working with neural networks in art investigation that I'm part of. I'm not against it. I'm very for it because it does magics in some sense, in many cases. But the interpretability is problematic there. So it might be that neural network would do a better job at estimating to which cluster a specific mystery tooth belongs to, maybe. However, it's hard to quantify what's the certainty of this outcome once you're using neural network. And in these works, we're trying to do we're trying to get a scientific observation. Scientific in the sense that I can say that the p-value that this is more similar to group A than group B is 0.0002, something like that. Okay. For example, in the case of the tooth, of the primate's mystery tooth, this tooth is coming that I described. So the common knowledge about the migration of primates to Madagascar says that around 40 million years ago, some monkey jumped on a raft and reached Madagascar. And then in Madagascar, you have lemurs evolving, only in Madagascar. And in Africa, you have other types of primates, which are lorises. And they found a tooth in the age of 20 million years on Africa, which somehow looks to them as a tooth that resembles more lemurs than lorises. So it should have been found on Madagascar, though it is found on Africa. So now, how do you quantify that? That's the main question here. How do I quantify that? How can I give a p-value to their observation? Can I say something scientific about that? Not just, it looks like A, not B. And what we found that with very high statistical significance, this is coming from the distributions of the lemurs, not lorises. And this might change the view of when primates migrated to Madagascar. So maybe a neural network would give me a better result in classification. I'm not saying no, because they have proven to be very strong tools. But how can I quantify that? That's something that I would like to know how well it does. I hope that answered the question.
Well, it answered partially because you define a distance and they define a distance. So, and then you're doing statistics on the distance and they're doing statistics on the distance. So you end up having a distance between each pair of samples and some certainty on how much you believe this distance in both cases. But again, we can discuss that separately.
Okay.